Welcome back to Visual Civil. In this part 1 video, we are exploring the intricacies in design of continuous RCC slab. Whether you are a student, a professional, or just a construction enthusiast, this video is packed with valuable insights and practical tips. We will cover everything from load calculations and reinforcement detailing to compliances of Indian Standard Code. So, grab your calculators and let's get started on creating strong and durable slabs that stands the test of time. Don't forget to like, subscribe and hit the bell icon to stay updated on our latest videos. In wall-supported and beam-supported slab floor system with steep beams, the slab panels are generally continuous over several supporting walls or beams. When each slab panel's aspect ratio of longer span to shorter span is greater than 2, then the bending of slab is predominantly in one direction as shown in this figure. In such cases, the slab is called as one-way continuous slab. In this type of slab, the distribution of bending moments across different panels under design loads can be calculated by using various structural analysis methods. For the ease in computations, a 1 meter wide strip is typically considered for analysis and design. In case where more exact calculations are not expected, the clause 22.5 of IS code lists the moment coefficient as well as shear coefficients in table number 12 and 13 for the continuous beam. Same coefficients can be used for continuous slab also. The values computed using these coefficients are close to the exact values of a bending moment and shear force obtained from rigorous analysis. These coefficients are applicable for uniformly loaded one-way continuous slabs and beams with at least 3 spans which do not differ by more than 15% of the longest. For negative moments at support where two unequal spans meet or in case where the spans are not equally loaded, the average of the two values at the support may be taken for the design. It should be noted that the moment coefficients have been derived assuming unyielding supports. Hence, the use of these coefficients is justified only if the supports are wall or beams that are adequately rigid. Now, let us try to understand the bending moment coefficients in table number 12. The table categorized the coefficients in two categories, that is, span moment and support moment. Span moment coefficients provide values for moments near the middle of end span and at the middle of interior span. Whereas support moment coefficients are used to determine moments at the support adjacent to the end support and at other interior supports. A positive sign of the span moment coefficient indicates a sagging moment, while a negative sign of support moment coefficients denotes a hogging moment. Here, separate coefficients are given for dead load and imposed or live load. For example, in span moments near middle of end span, the coefficients for the dead load and imposed load are 1 by 12 and 1 by 10 respectively. Whereas at middle of interior span, they are 1 by 16 and 1 by 12. At support, next to the end support, the coefficient for dead load is minus 1 by 10 and that for the imposed load, it is minus 1 by 9. At other interior support, they are minus 1 by 12 and minus 1 by 9. Now, to obtain the bending moment, these moment shall be multiplied by the total design load and effective span. So, let us assume WDL as dead load intensity and WIL as imposed load intensity and L as effective span. Therefore, total design dead load and imposed load are WDL times L and WIL times L respectively. Now, let us multiply these coefficients with total design load and effective span. After simplifying, we get the expressions for the span moments and support moments as shown here. Similarly, the shear force coefficients for end support, next to the end support, and other interior supports are given in the table 13. For obtaining the shear force, these coefficients shall be multiplied by total design load. Now, let us try to understand the computation of effective span. For continuous spans, the effective span depends on the relative width of support as per clause 22.2b. If the width of the support is less than 1/12 of the clear span, then effective span shall be computed as per clause 22.2a. But if the supports are wider than 1/12 of a clear span or 600 mm, whichever is less, then effective span shall be computed as per the clause 22.2b. The factored moment mu at any section is obtained by detailed analysis using any analysis methods or using moment coefficients if appropriate. The thickness of slab is usually governed by limiting L/D ratios for deflection control. In this regard, the end span whose one end is discontinuous is more critical than the interior span. As the midspan moment in the end span is significantly larger than that in the interior span, the end span will require a larger area of a tensile steel which govern the thickness based on maximum L/D ratio. Generally, the same thickness is provided for the interior spans also, unless there are many interior spans involved, whereby a separate and lesser thickness may be specified for the interior span in the interest of economy. The required reinforcement for the calculated sagging and hogging bending moment at the different midspan and support section should then be determined. As per SP 34/1987, this reinforcement may be provided in one of the two alternative ways as shown in figure A and B. In the first method, separate bars are used for the top reinforcement and the bottom reinforcement. Alternatively, in the second method, the top bars over a support region may be provided by bending up alternate bars of the bottom reinforcement from either side of the support with additional top bars if required. The calculated spacings required theoretically in different spans or a support region are not directly provided. In practice, it is desirable to correlate the spacing requirement at the different locations of the continuous slab and to provide either the same spacing or a fraction or a multiple of it in all spans or support so that placement including bent up over support becomes convenient. That's a wrap on this part 1 video. In next part 2, we will implement all the learnings of this part 1 in a design numerical. If you found this video helpful, give us thumbs up and don't forget to subscribe for more design insights. Drop your queries or experiences in the comments below and we might feature them in our next video. Until then, keep learning.